Okay, for this chapter on further differentiation part 2, we only have two learning outcomes, and we will look at the first learning outcome will be parametric equations and how to determine first and second derivatives for parametric equations. The second learning outcome will focus on application of differentiation, which utilizes this parametric equation in terms of application involving displacement, velocity, and acceleration. And also, the second part of the application will focus on how to determine related rates of change. Dear students, we will actually look into parametric equations. So we normally write y in terms of fx, but we can also write x and y as a function of a third variable. So mostly in your textbooks, they use the term, the letter t. So for example, if you have equation x in terms of t and this is y in terms of t, these are called parametric equation simply because x and y is written in terms of a third parameter, which is t. So each value of t will uniquely define a point or represent the value of x and y on a curve. So for example, if you consider the straight line equation as such stated, then this is how the line is drawn. You represent it with a set of axes, x and y, and the same line can also be represented by the parametric equation. So for example, say you write x in terms of t and y in terms of t. This is what is meant by two different parametric equations. And for every value of t, that means each value of t will uniquely define a point on the curve. So for example, when t is 1, you get a point of 8, 0 by substituting t1 into x and y. And then when t is -1, you substitute into this equation and you will get another 0.60. It's also possible to eliminate t from a parameter from a pair of equations. So for example, if you consider the parametric equations from the previous straight line example, and x in terms of t and y in terms of et, so in order to eliminate t, there are some simultaneous equation or substitution equations method involved. So for example, you can make t as the subject of equation in x so that you can substitute t in terms of x into the equation y in order to eliminate t. So this is how you can do it. Make t as the subject of the equation of this, the first x in terms of t, you make t as the subject of equation and then substitute this into the y equation here. So substitute t as x over 4 minus 1. And then you try to rearrange it, you should be getting the original straight line equation provided just now. So this equation has a term called constraint equation. So it's known as constraint equation. Please note that the parametric representation of a curve is not unique. For any that means for any function y equals to fx, you can define a parameter in terms of any other parameter. It can be u, it can be t, it can be w, it can be z, anyhow. So your understanding is you need equation x in terms of u and y in terms of u in order to make y equals to fx to be defined. So for example, the pair of parametric equation also represent the same line as before. Instead of t, you write it in terms of Hi, now we will look at another example of parametric equations, which are actually parametric equations involving a circle. So for this case, when you consider the pair of parametric equation as x equals to this and y equals to this. So recap back, in order to get a circle equation, you need to have an equation which involves the center and also the radius. So it's the general equation is x minus a squared plus y minus b squared equals to r squared. So you try to write this in terms of that equation. So you have x and y. So from here you can derive that x minus 4 is r cos theta and y minus 3 is r sin theta. So this is similar to x minus a and this is similar to y minus b. So as I said just now, x minus a squared plus y minus b squared equals to the radius. So in this case, the equivalents are r squared theta, r cos theta squared, and also r sin theta squared. We can further simplify this, and it will become x minus 4 square, y minus 3 cube. I brought this one over on the left hand side. Cos square plus sine square is always 1. So when you factorize r square as a subject, it becomes r square multiplied by cos square plus sine square, which is 1. So it will reduce to r square. So this is a circle equation with the center 4, 3, and the radius is r. So this is also known as another constraint equation similar to the straight line equation in the previous example. The parametric equations are known as the freedom equation. Right? We will now look at more example to determine the constraint equation of the locus defined by the parametric x and y. So what is meant by constraint equation? You're given x in terms of t and y in terms of t. You have to actually determine y in terms of x and then sketch the curve. So x, y. So the easiest way would be to get y in terms of x would be squaring both sides. So the methods can vary on how to get y in terms of x depending on the x and y given. So when you square both sides, you get this. And the next step, since you have t square, and you have t square, and you have t negative 2, t negative 2. So it will be wise to actually subtract these two equations. Okay? So the first one minus the second one, you will get x squared minus y squared. This function minus this function, you will actually get 4. Because you eliminate square, square, and a negative 2 powers. And so therefore, this is a constraint equation of the locus defined by this parametric. So if you want to have fun drawing it, you can actually sketch this. You can even use the equation grapher or the Desmos graphing function on your phone. And you can actually graph this equation. So now we will look into how to determine first and second derivatives of parametric equations. So when you have x in terms of t, y in terms of t, and y is fx, then it's possible to determine f prime and f double prime x by applying chain rule. So for example, f prime x is dy dx. So dy dx can be obtained by using the chain dy dt multiplied by dt dx. Because we can determine dy dt from here. Y, when you differentiate y is dy dt. When you differentiate x is dx dt, and you can flip it to divide it. So in other words, the simpler way to write out the formula is simply y prime over x prime. So dy dx is, for parametric equations, is y prime over x prime. Whereas for the second derivative, d square y dx square, we will actually use, these are all mathematical terminologies, yeah? So simply means you differentiate the y again, and when you differentiate the y again, it's as if it can be shortened down to this formula, differentiate y, divide by differentiation of x. Okay, so this can be further wrote in an easier way using the Leibniz notation, y prime x prime, and you can summarize it in this term. So this is the formula for you to get the second derivative, which is y double prime multiplied by x prime minus x double prime multiplied by y prime over x, differentiation of x cubed. Yeah, you can combine square and x prime, it will become x prime cubed. So as you can see, you can actually summarize your second derivative formula in terms of using the Leibniz notation, y double prime times x prime minus x double prime times y prime over x prime cubed. So for example, find f prime and f double prime when x is such and y is given in terms of t as well. So your first task will be f prime based on the previous formula in the previous slide. So f prime is y prime over x prime. So you identify x prime and y prime first. So you have got y prime will be negative 60 and x prime is actually 4. So that's the easier way you see to derive your first derivative of a parametric equation. And you can simplify it if you want to. And the second derivative, based on the formula up here, you see y double prime. If you differentiate y double prime again, you will get negative 6 y double prime. X prime is 4. So y double prime times x prime minus x double prime. When you differentiate 4, first derivative gives you 4, second derivative will definitely give you a 0. So x double prime is 0 here, multiplied by y prime is definitely negative 60. So this part will be 0. So you can reduce and then your answer to over 4 cubed. 4 is obtained from the first derivative just now. Substitute 4, x prime is 4 cubed. And your answer can be reduced further to negative 3 over 8. So we will look into the next example. If you're given a locus which is represented by parametric equations x and y, and you need to solve these three questions. First, find the point on the locus corresponding to a parameter value. Theta is pi over 2. So this is as simple as substituting theta as pi over 2 to determine the value of x and y. And then when you need to find the gradient is simply f prime x or dy dx. So you need to apply the dy dx formula. Okay. And the third one is actually find concavity. Concavity here, it relates the second derivative. So d squared y dx squared. So we will apply what we learned just now. Okay. So you substitute x theta as pi over 2 into x and also y in order to get a point. So thus the point on the locus is actually 3, 9. Okay. Part B, we will actually we need to identify the dy dx. So dy dx is simply y prime over x prime. So from the original x and y equations, x prime is negative 5 sine theta and y prime is 5 cos theta. So f prime is y prime over x prime, and you can further reduce this to 1 over tangent, which is negative cotangent theta. So when you substitute pi over 2, you will actually reduce your answer to 0. So therefore, when the dy dx is actually 0, therefore the tangent is actually horizontal. For the part C, we need to determine second derivative. So second derivative for parametric equation involves x prime, y prime, x double prime, and y double prime. So it will be useful if you identify everything x prime, y prime, x double prime, and y double prime. So they can substitute it into the formula straight away. So we sub it into the formula. Y prime, x prime, so sorry, y double prime, x prime minus, this will be x double prime, y prime, okay, over x prime cube. So substitute it and you will reduce your answer to this part. Okay, once you reduce your answer to this part, you can actually simplify it further and you will reduce your answer to, and here when your theta is actually pi over 2, your f double prime max is negative 1 over 5. Therefore, your f double prime max is less than 0. Less than 0 normally represents a maximum point. So your curve is actually concave downwards.